Hello friends. Now today we will start with, we can say, the chapter number 2, electric potential. You know that very well present time, because of this lockdown scenario, we can't meet face to face because of some, you can see, the social distance, and that's our duty also. So time is very important for us. No doubt the situation of each and every student same, but we would like to think about, we can say, that you. So that's why, without wasting of time, we are thinking about, and we start this chapter number 2, electric potential. If you think about the weightage, approximately 9 to 10 marks. You know that in this entire physics there are 5 to 6 chapters are very important, and this one is the one of the very important chapter out of these 6 chapters. If you cover this chapter very well, then board wise, JEE NEET wise, and you can see about your competitive, your computer, you can see that also laggard in this type of chapter, because this is very large, fundamentally very strong, numerically, theoretically very supreme chapter. So we'll start with this chapter, electric potential. What do you mean by electric potential? To understand this point, we start with, we can say, that one point. You can see here in this diagram a three-dimensional coordinate system I have shown, and consider a capital Q charge. Suppose this is the positive charge. Consider a plus Q, that means the positive Q charge, which is already situated at the center of this origin point, or at the origin point of the coordinate system. Now you can see this one is the positive charge. Obviously charge producing a field, you know that very well. If you are just in front of you, sorry, in front of me, then obviously I will ask question to each and every student. But what do you mean by this plus Q charge producing field? It is electric field. And what's the direction of electric field due to this positive charge? Positive charge, that's why electric field always outward. So this is the direction of this electric field, you can see in outward direction. Now one point is clear, just around this plus Q charge there is electric field. This plus Q charge producing electric field, that's why it is called simply source charge. You know that very well because of chapter number 1. Now we will consider 2 points inside this electric field. These are the 2 points, point P and point R, and let at this point R there is a small q charge is situated. So small q charge is situated at this point capital R. Small q charge, obviously the magnitude of this small q charge is smaller than that of this plus q charge. That means this is your test charge, nothing, you can see this is your test charge. You have idea about test charge and source charge. So test charge is situated at this point R. Now we would like to move this test charge from point R to P. Once again, don't forget this entire, you can see the scenario inside the electric field. This test charge is situated at this point capital R, but it is already in the electric field of this plus Q charge. Now what's the most important target? The target to move this test charge plus small q from point R to P, and that's why, you know that very well, we have to think about one most important point. You know that very well, to move this charge from point R to P, we have to do some work, and whatever the work is required, how can you calculate this work? Now before moving towards the calculation of the work, we'll think about something different, or I can say that something extra. You know that work, if you remember this quantity, like you can see that work, then work is associated this word, I can say that potential. Check it. If you remember chapter number 8, standard 11, the gravitation, then you know that in this chapter there is one quantity, gravitational potential. What do you mean by gravitational potential? Gravitational potential, that means, you know that very well, work done per unit mass. You can see mass. If you remember the definition, then work done required in moving unit mass from infinite to given point in the gravitational field against the gravitational field is called the gravitational potential. Once again, work done required in moving unit mass from infinite to given point, but in the gravitational field against the gravitational field is called the gravitational potential. So gravitational potential, what is the short and sweet definition of potential? Gravitational potential, work done per unit mass. So we are discussing for electric potential. So very easy definition of electric potential, work done per unit charge. So here you can see that charge is just in front of you. At present time, instead of unit, I have considered plus q charge. So whatever the work done required in moving this plus q charge from point R to P, it leads towards very important word, and it is electric potential. So first of all, we would like to think about the calculation of work done. So you can see what's the target, very important. Once again, if you think about the entire scenario, there is a plus q charge. Because of this plus q charge, electric field is produced. Inside this electric field, we have considered 2 points P and R. At this point R, there is a test charge, and now we would like to move this test charge from point R to P. And for that, we have to do some work. And now we are moving for this topic, that means for this case, like calculation of work done. So how can you calculate work done? You know that very well. This entire path R to P, to calculate this work done, this entire path R to P is divided into many small segments. You can see that line segments like this one. And what is the, we can say that the length of this segment, very small segment, let the length of this each and every segment is dr. And you know that very well. What is the method to calculate the total work done? First of all, we have to think about very small work done for very small displacement, and then we'll think about the entire work done by taking summation, and this summation is converted in the form of integration. So first of all, what is the, we can say that work done, I can write small work done for very small displacement dr, and it is supposed dw. So what's the dw? dw is equal to force. What's the formula of the force? Force into dr, force. You know the general formula of work done, F dot dr, force displacement dot product. Okay, but here dr, that means very small displacement, dw, that means small work done. So what do you mean by F? F, this is the very interesting point. So just consider here. You can see here plus q charge, here plus capital Q charge. Both are positive type, like charges. So obviously, whatever the force acting on this test charge, because of source charge, it is obviously repulsive type. And what is the direction of the force? Repulsive, you know that very well. So this is the direction of the force. So whatever the force acting on this test charge, because of this source charge, it is already, you can see that in this direction. That means away from this source charge. This is your F electrical, that means force due to electrical field. But you can see we have to move this test charge from point R to P. So we have to move in this opposite direction. So obviously, here very important point, we would like to move this test charge from R to P with constant velocity. That means not accelerated motion but constant velocity. Obviously, to maintain velocity constant, we have to apply same magnitude force but in opposite direction, and this is, you can see that same magnitude force but in opposite direction. This force is applied by you externally, that's why it is called external force. So this is the force which is applied by you, this is the force which is produced due to, we can say that, electric field of the charge. But these both forces are equal in magnitude, opposite in direction. That's why we can move this plus q charge from point R to P with constant velocity. So from this entire discussion, I can write one very important point. Here F external is nothing but F electrical, but in opposite direction. You can see both are in opposite direction. But now here you can see small work done. We would like to move this positive charge from R to P. First of all, we have considered very small displacement dr. So small work done for very small displacement dw, but this force now F external, because this is the force which is applied by you, but F external is equal to dw minus F electrical dot dr. You can see F external is equal to minus F electrical. So this is the work done. This one is the work done which is required for very small displacement of this test charge, for, or we can say that for dr displacement. So we have calculated, or I can say that we have obtained the formula for the small displacement, but this is the small displacement. Similarly, we can also obtain dw for next dr, dw for next dr, dw for next dr. In this way we can obtain total work done. So what is the total work done? So total work done in moving plus q charge from point R to P, it is W. So it is W, that means the integration of this dW. But what is the dW? It is F electrical dot dr, and there is minus sign. And what's the, we can say, the limit for this integration? You can see we are starting from this R. Our journey started from R and completed this point P. So with respect to this origin point, I can say that R to P. So here R to P. Okay, but here F electrical. What's the formula of the force acting on any charged particle because of electric field? Anybody? You know that force acting on charge because of electric field. It is given by equation. You know that W is equal to R to P. There is, you can see that minus sign. F electrical force, F is equal to QE. You know that force acting on charge because of electric field, F is equal to QE. So we'll set up here F electrical is equal to Q into E. That means electric field dot dr. Ready? So very interesting point. W is equal to minus Q R to P E dot dr. If you move this Q in this direction, that means in opposite side, then W upon Q minus R to P E dot dr. Most IMP formula we have derived. But if you analyze this work done, we have calculated this work done. This is the, you can see that work done, but this work done in moving this test charge from point R to P. So I can write here work done for R to P, work done for R to P, work done for R to P. So what do you mean by this entire point? Anybody? WRP by Q. It is called work done required, or work done in moving unit positive charge from R to P. This is the work done per unit charge. What is the meaning of this point? It is called simply work done per unit charge. You can see most IMP, or work done per unit positive charge. You can see very important point. This is work done per unit positive charge. And what do you mean by work done per unit positive charge? It is called simply electric potential. So work done per unit positive charge, it is also called electric potential. So in short, in very easy language, I can say whatever the quantity we have derived, it is your work done per unit positive charge. That means potential in moving charge from R to P. So VRP minus P to R, R to P E dot dr. Keep in mind, potential is denoted by V. So we have written here VRP minus R to P E dot dr. Very interesting point. Now, before moving towards the next point, we will revise the entire story. Just concentration required. This is, you can see that one of the familiar point like gravitational potential. Keep in mind, if you remember this theory, gravitational potential, chapter number 8, we derived this formula of gravitational potential minus Gm upon R. Keep in mind, this is the most common formula. On the surface of the earth, gravitational potential minus Gme upon Re. Ready? And at that time also we perform the same story. So similarly here, so just concentration required. Electric potential. One point is clear now. Potential, that means work done required in moving charge from one point to other inside the electric field. And you can see this minus sign also indicating against the electric field. Anyway, friends, now just concentrate here. In this diagram, a plus Q charge is placed at the origin point. Obviously, because of this plus Q charge, electric field is produced. I have represented electric field Y outward because of positive charge. Now inside this electric field we have considered 2 points P and R. You can consider any 2 points arbitrary, but I have considered P and R as per textbook. Now at this point R there is a test charge. That means plus Q charge is here situated at this point R. We would like to move this test charge from point R to P inside the electric field. But you can see this test charge is placed here, then it experiences some force. Force because of this positive charge. This is, you can see that electrical force because of this positive charge, F electrical. And this is the formula, F is equal to QE. And you know that very well. What is the direction of electric force acting on any positive charge? Because of electric field, it is always in the direction of electric field. For negative charge in opposite direction. Okay. Now, test charge is situated here. We would like to move this test charge from R to P. How can you calculate this work done? Because work done is required in moving this charge from R to P, and work done is one of the very important quantity for this entire discussion. Don't forget potential. Then you have to think about work done. So here we would like to calculate work done in moving charge from R to P. So this is the method calculation of work done. You can see first of all this entire path R to P is divided into many small segments of length dr, and we will consider work done, I can say small work done only for very small displacement dr. That the small work done for very small displacement dr is dw. So dw is equal to F dot dr. Here F is the force. This is the force which is applied by you. It is called external force. Why external force in opposite direction of force due to electrical field? Because we would like to move this test charge, we can say that with constant velocity. Because of these two forces are equal in magnitude and opposite in direction, we can easily satisfy this condition. So now you can see instead of F electrical, we can consider F external. So F external, but F external is equal to minus of F electrical. So instead of F external, I have written F electrical minus. So this is the very small work done for very small displacement. Similarly, we can think about next dW, next dW, next dW. So how can you find total work done? So total work done in moving plus Q charge from point R to P is the summation of this all dW, and this summation is converted in the form of integration, you can see, and integration from R to P. So R to P, dW already we have found, minus F electrical dot dr, minus already out of integration. Why here I have to write RP, the work done required in moving charge from R to P. This is work done only for R to P, from R to P. That's why RP, you can see that RP. Minus sign. What's the formula of F electrical? F electrical is equal to QE. You know that very well. Q into E, Q out of integration, E dot dr. Q already here, so WRP by Q is equal to minus E dot dr. What is the meaning of WRP upon Q? It is called work done per unit charge. And you know that very well, work done per unit charge is nothing but it is called electric potential. So very short and sweet definition of electric potential, the work done required per unit positive charge, it is called electrical potential. This is short definition. We will derive, we can say the perfect definition also. So this is your potential. So potential is denoted by V. So VRP. What do you mean by VRP? There are three different meanings. We'll discuss, don't worry. So VRP is equal to minus R to P E dot dr. This is the general formula of potential. In short, I can write potential V is equal to work done per unit charge is equal to minus R to P E dot dr. So now, if you observe this equation, then potential is equal to work done per unit charge. Potential can also be defined in the form of this integration. What is the meaning of this? You can see chapter number first, Gauss theorem. Remember, as per Gauss theorem, flux phi is equal to E dot ds. What is the meaning of this point? It is called surface integration of electric field. While here E dot dr, dr is the line. It is called line integration of electric field. So very interesting point, electric potential, that means line integration of electric field over the given path. Here given path, that means R to P. Very important formula we have derived. So there are two different meanings of electric potential. Number one, work done per unit charge, And number 2, the work done potential charge. And number 2, line integration of electric field from path R to P or for given path R to P. So very interesting point. V is equal to W by Q and integration of E dot dr. So print here minus sign indicating opposite direction of electric field. You can see that here work done is done against the electric field. So this is the basic point I have discussed. The first point we have discussed. Now we'll think about some very important next points, but first of all analyze this first point. Turn by turn we'll discuss. Short we can say the range will derive, not at all we can say the movement each and every segments. So just take your time, analyze, and then we'll think about the second lecture you can see. Thank you.